Okay, let's take a look at some example problems from your textbook. They call them the warm-up exercises, and they appear in the at the end of your chapter. So let's go ahead and take a look at those and see what they have to offer us. So number one, these are mostly all math review. Number one says, let's convert the numbers A and B shown to scientific notation. So in both cases, we've got decimal representations. We'd like to convert them to a decimal notation. So A, 5,068 and 17, and B, the decimal 0.000309. And notice how we put a little space in here. The space is always good to help you identify quickly what the magnitude is of the number that you are in fact looking at. So if we take the first one, convert 568,017 to a scientific notation, the explanation here says the number given, 568,017, has 6 significant figures. So we're going to find out during this course that dealing with accuracy and significant figures is very, very important. So it's worth starting off with this one to get an idea of what we're looking at. So every number, every place in this number is significant. So every one of the digits count. So we will retain that 6-digit significant figure in our answer when we convert it to a scientific notation. So in this case, we're looking at converting this number to something that has a power of 10 in it. So if we look here down at the answer, our answer comes out to 10 to the 5th. So this requires us to do nothing more than move the decimal 5 places to the left. So in this case, although we don't have a decimal showing here just after the 7, it's understood. So if we take that understood place where the decimal is and move it 1, 2, 3, 4, 5, between the 5 and the 6, we end up with an answer of 5.68017. Notice we adjusted the 0 up, so we have these groupings of 3 and then no 0 after. We don't put a 0 after it because there's no 0 in the original problem to identify it as a significant figure. You'll notice that 0 is considered to be significant. So 5.68017 times 10 to the 5th is our converted value to scientific notation. So now let's look at the fractional decimal number, 0.000309. So in this number, we only have 3 significant figures. The zeros, the leading zeros after the decimal point, are not considered significant figures. So again, we will retain the value of 3 significant figures when we convert the number to scientific notation. So now in this case, we're going to move the decimal point 4 places to the right. So 1, 2, 3, 4. The decimal point is going to be between the 3 and the 0, and we are going to then convert it to 10 to the minus 4. So when we move it in the direction to the right, it becomes a negative exponent. So you're going to be seeing a lot of that and doing a lot of that throughout the course. Number 2. Okay, this becomes very important in understanding this concept of dimensional units or unit dimensions. So in this case, we have 3 dimensions that we look at primarily in physics: mass, length, and time. So we want to simplify the expression in terms of the dimensional units, mass, length, and time, by m, l, and t. So we have mass, length squared, divided by time cubed. We're going to multiply that times time divided by length, and then we are also going to multiply it times time. So how do we gather the terms here with these dimensional units here and make some sense of what we can do to simplify the expression. So in doing this, we're going to gather all of our terms. There's only one unit of mass, there's a squared unit of length, and in this case, there is a squared unit of time in the numerator. So time and time. In the denominator, we have a cubed unit of time and a single unit of length. So now, when we go through and do our dimensional analysis simplification, we are able to start canceling those values that are exponential. The mass we leave alone. We have 1 unit of length in the denominator. We have 2 units of length in the numerator, so we can cancel out one of those lengths, and that just leaves us L. And then we have 2 units of time in the numerator and 3 units factors in the denominator. So when we cancel those out, we're left with ML divided by T. Something that we're going to learn later is ML and T are the units for momentum. So whenever you're checking your answer, you always want to check your answer and make sure that your factor units are correct. Let's take a look at number 3. Number 3 says simplify the following expression combining terms as appropriate and combining and canceling units. You notice in your text, and I've put it here, which section this comes from. So we have 7.00. Again, we're looking at maintaining our significant figures here. Meters per second squared. We're going to find out later meters per second squared is a value, a very important value of acceleration. 1.00 kilometers by 1.00 times 13 to the third meters. So we have basically meters over meters. This is a factor of 1,000. So we're going to be able to simplify those later. And then in the last expression, we're going to multiply it by 60 seconds in 1 minute. So, and that whole value is squared. So in this example, we've got seconds, 60 divided by 1 minute as a conversion. 1 kilometer divided by 1 times 10 to the third meters is a conversion. So what does it look like? Well, examining the expression shows that the units of meters seconds squared both appear in the numerator and the denominator, and therefore cancel out. We combine the numbers and units separately, squaring the last term. So units, like numbers, can be gathered together and treated individually, and then later end up being combined back to your full numerical values. So 7, 1 over 1 times 10 to the 13th, 60 divided by 1 minute. All of those terms are gathered together as values, constant values, that we can deal with mathematically. And then on the other side, we've got all of our unit values that we can handle almost like math as well. We can start canceling them out. So that when we're done, you can take this value, 7 times 1 times 60 squared, divided by 1 to the times 10 to the 13th, and we end up with a hard value of a constant, 25.2, and then our units, kilometers by meters, or by minutes squared. So in this expression, we can see all we had left was kilometers per minute squared, which ends up being a acceleration value. So that's the first 3 of the warm-ups. If some of it didn't make sense to you, pull out a piece of paper and work through it step by step to refresh your math skills and your analysis skills, because you're going to be doing this over and over again in this course. So next we'll come back with number 4. Number 4 will be looking at doing some more conversions.